Hey scholars, this is Mr. I with you. So we're talking, we're going to be talking about section 8.5, which is the binomial theorem. Now you may be thinking, oh, what is that binomial theorem? What are you talking about, Mr. I? Well, what the binomial theorem is just basically a theorem that allows us to do the following the easy way, which is this. If you come with me over here, if you have a binomial meaning, remember, two terms, one term, two terms, right? So if you have a binomial, for example, and you raise it to the 0 power, well, and it says, oh, that's 1. Well, yeah, you're right, it is 1, because any number to the 0 power is always 1, right? Now, but what if I take, let's say, the same binomial and I raise it to the first power? Well, you know that anything to the first power is whatever that number is, so it doesn't change. It's just x plus y, and you are correct. That is, right? No problem. Now, what if you raise the exact same binomial or another binomial to the second power, right? Well, if you raise this to the second power, you guys will remember that that means x plus y times x plus y. And we all know that x plus y times x plus y, we use FOIL, and then we get the final, basically the final answer, or the expanded form of that, which ends up being x squared plus 2xy plus y squared. But what happens as we keep increasing on our exponents? You will see that, for example, x plus y to the third power is going to be x plus y times x plus y times x plus y. And if you multiply all that out, it's going to give you a big, long, ugly thing, right? And then you have to combine like terms and all that. So it's going to start getting longer and more complicated, as you can see. For example, x to the fourth, this is what it would factor or multiply out to, right? So now, there is a pattern to this. So that's basically what the binomial theorem helps with. There is a pattern to doing this in a systematic or easier way than actually multiplying them all out and getting a big, long, ugly thing. So for example, let's talk about some of the patterns that are in here, just to point them out, and then later on we're going to be working out examples on how to come up with these things, okay? So for example, one of the things that you can notice is that the number of terms in your expanded form, the number of terms, it's always one more than your exponent. This is what I mean. For example, notice over here, 0 power. We end up with 1 term, right? So, look over here. The power is 1. But how many terms do we end up with? 2. There's always one more term than your power in the final answer. For example, on this one, notice it's squared. How many terms do we end up with? 1, 2, 3. Whoa! Okay, well what about this one? There's 3 terms, so that means we must have how many? 4. You're right, look. 1, 2, 3, 4 terms in our final answer. Well, to the 4th power, we're going to have one more, right? So 5. Look. 1, 2, 3, 4, 5 terms. So that pattern continues throughout. No matter what exponent you use, there's always one more term than your exponent. So if I tell you, for example, how many terms, if you raise this to the 10th power, you know that must be 11. You're right. There's always one more term than your exponent. So those are some of the neat, or one of the neat patterns that is in these types of problems. So now, let's talk about another pattern and see if you notice anything. But one of the things that happens, I'm going to use, for example, this one, because it's very noticeable, is this. Whatever's on the left, like your x over here, notice that if this is to the 2nd power, it starts to the 2nd power, right? There's your 2nd power. And then as you move one over, notice that your powers actually start decreasing by 1 to the 1st power. And then technically it will be x to the 0 power. But you know x to the 0 power is 1, so it's not there. But technically, you know, you could, I guess you can make a case and put it there. But it's really 1, so it's going to turn into just whatever's left over. So let's follow that pattern over here. Notice x plus y to the 3rd. There's your x, right? So you start off to the 3rd power, then it decreases by 1, then it decreases by 1, right? So then that's x squared, x, and then it's going to be x to the 0, in other words 1, so we don't even write it because we know it's just 1. And then same thing over here, notice x to the 4th. You start with x to the 4th, x to the 3rd, x squared, x to the 1st, and then x to the 0, which is 1, so we don't write it. Right? But that's for the x, the term, the first term. But look what happens to the 2nd term. There's a pattern with that too. Notice that this is our 2nd term, right? Now, it's squared, but look what happens. On your very first term, you never have the second one there, right? But when you move on to the second one, notice how it's, instead of decreasing, it's actually increasing, or it starts increasing by 1. This is y to the first, y to the second. And obviously you could think of it as y to the 0 there, but like I said, that's 1, so we pretend like, well, you know what, it's just 1, so we just don't write anything there. Now look at y to the third. Remember, this technically will be y to the 0. It goes backwards. And then look, y to the first, y to the second, and then y to the third. We go to the fourth one, same thing. Y to the 0, y to the first, second, third, and fourth. So as you can see, there is a pattern. There is a pattern here. There's a pattern with the number of terms. There's a pattern with what exponent goes in each of the variables for both of them, for the x and the y. Now, there is also a pattern, which is, if you will notice that the sum of the exponents of every term is always, always, always your power. Check this out. This is one term right here. What's the power? 1, right? What was my original power? 1. Look at this one right here. What's the power? 1. 1. Oh, okay, cool. But look at this term. The power is 2. What was my original power? 2. Look at this one. The power is 1. The power is 1. 1 plus 1 is 2. Same thing right here. Now let's see if it works for these, right? Let's see. Well, this is to the third, to the third. Oh, okay, cool. Now let's look at this power. This is the power of 2, the power of 1. 2 plus 1 is 3. Oh, cool. Look, power of 1, power of 2, add them up, 3. And then same thing for there. And if you check on the last one, it's also the same thing. So these are nice, neat patterns that happen on this. And then what we're going to do is, having a basic understanding of how these patterns work, it's going to help us actually add numbers to all of this and be able to expand them efficiently and make sense of this without actually doing all this work. Because remember, to end up, for example, with an answer like this, it will take a lot of work, a lot of combining like terms. So if we follow the binomial theorem, that's going to help us come up with this in a quick, efficient manner.